Okay, I'm very happy to introduce the first speaker, Moon Han-bom from Hodam University. After his PhD in Seoul National University, and he is working in mostly in United States. So today he will give a talk on point configurations, phylogenetic trees, and dissimilarity vectors, maps. Okay, let's welcome him.
Okay. Thank you very much for the introduction, and thank you for coming in such an early morning. I'm sorry, I changed the title of the talk slightly, so that the new title is point configurations, phylogenetic trees, and dissimilarity maps. So I should say that this talk, the topic would be slightly different from many other algebraic geometry talks. I choose this topic because I just wanted to introduce some very different kind of algebraic geometry to all of my friends around the East Asia. So all I want to say today is joint work with Alessio Caminata in Italy, Noah Giansiracusa, and Luca Sciapolo in Sweden. Okay, so let me start with the statement of main theorem. I'm going to explain the main object and all of the terminologies later, but here is the main theorem. So let's fix the number n and r, which is between 2 and n minus 2. Then the weighted R dissimilarity map embeds the space of phylogenetic trees. Of course, I'm going to explain what it is. It has a tropical variety, which is the tropicalization of the variety of point configurations relying on a rational normal curve. Moreover, we can say a little bit more about the tropical variety TRN, a vector in n to the R dimensional vector space is in TRN if and only if it satisfies two very explicit conditions. So I'm going to explain what it is. So this topic is related with a lot of different topics, including combinatorics and computational biology and tropical geometry, and even classical algebraic geometry date back to 1920s. So it is based on the result in 2 papers. So you can find it if you're interested. So first of all, let me start with some background. Why do I care about this problem? So that the main object is a matrix trees. So that we say a tree is a graph G with a cycle, and a matrix tree is a pair of graph and a function L, which is a function assigning for each edge E, we are going to assign a positive length. So L is really the length function. We are going to call an end vertex, like here. There are 7 end vertices in this example. We are going to call them as leaves. So as you can see, all of the edges have some proper assigned numbers, but they are lengths. Okay. But this matrix tree naturally appears in the branch of computational biology, which is called phylogenetics. Just to think about the situation, suppose that we have 10 or 100 different species, like mammals, fish, reptiles, etc. From our science class in high school, we know that everything is branched out from the common ancestor. By evolution, everything is branched out from a single origin. And what we want to understand is how the evolution actually occurs in history of life. So we want to describe it by using a nice tree diagram. So you can understand that at the beginning there was only one origin. It branched out into two different species, and the evolution continues. We have a lot of different species in the world. Okay, so in other words, the tree of life, which is called the phylogenetic trees, is another name of matrix tree in computational biology. Okay, now let's go back to the matrix tree. So here, this is the example I gave you before. When we have a matrix tree, then for each pair of leaves, like 1 and 5 here, then we may define the distance dij between these two leaves. So the idea is really simple. We are going to connect the unique path from the vertex 1 to another vertex 5. Then we can simply add the length of edges on the path. So for instance, in this example, excuse me, the distance from 1 to 5 is d15, which is 3 plus 2 plus 4 plus 1, which is 10. Of course, we can compute the same the number for any pair of leaves. Then if you compute and collect all of them, then we can make a finite length vector, dij. Okay. Well, then one thing which can be easily checked is that this vector dij indeed define a matrix on the finite set of leaves. And any matrix on the finite set which appears in this form is called a tree matrix. Okay, so the long story short, any matrix tree induces a tree matrix. Okay. Is it clear? Is there any question? If you're okay with it, then please thumbs up or nod, or please respond in your preference. Okay. All right. So here is a motivational question inspired from computational biology. So the question is, how can we recover the tree of life from the given set of species? So, well, in reality, we don't have this diagram, the tree diagram, phylogenetic tree. What we do have is just a collection of different species. What we want to understand is, from this data, we want to recover this phylogenetic tree. Well, in early 20th century, the only way people can do this job is just comparing the similarity in their appearance or behavior resemblance, something like that. But now we know that the genetic information is encoded in DNA sequences. So we can replace each species by a finite length vector or some numerical data. Then we can measure the distance between two species by measuring the distance between two vectors. So here is the question. Suppose that we have a distance vector, W, which measures the collection of distance between every pair of species. Then the question is, can we find a matrix tree such that the induces tree matrix is W? Does it make sense? Okay, so this was one of the most important problems in 20th century in computational phylogenetics. But a clear obstacle is the computational complexity. For instance, if we have 20 different species, then the number of trees with 20 different leaves is already larger than 10 to the 20th. So even finding the correct topology of the tree is already very difficult problem, and finding the distance between two, the length of each edge is also really complicated. Okay, anyway, so then let me reformulate this question in terms of more formal mathematics. So suppose that Tn is the set of all phylogenetic trees with n leaves, then we can that the computation of tree metric is indeed understood as a map from the set of phylogenetic trees to R to the n choose 2. So the idea is really simple. Take a metric tree, then we are going to compute the distance vector W, whose components are all Dij, the pairwise distance. This map D is called the dissimilarity map. Okay? And the questions we want to understand are the following. First of all, is the map D injective or not? So in other words, in the computational biology terminology, this question can be interpreted in this way. Suppose that we have a distance vector, then can we recover the topology and distance on the tree from the distance information of the DNAs? Yeah, so in other words, is there any ambiguity to recover the tree of life? Okay. The second question is, okay, suppose that this is true, then can we find the metric tree effectively? So this is a matter of quick computation. So can we do item 1 quickly in polynomial time, etc.? The third question is, okay, then what is the image of this dissimilarity map? Can we describe it easily, or can we describe it theoretically? All of these questions were very important and central questions in the late 20th century and early 21st century. I would like to say that the answers for these questions are already very well known. For instance, in 1971, a combinatorist Buneman answered the first question is yes. So there is only one way to recover the tree, theoretically. But for a long time, people believed that the recovery of the tree is really difficult problem. However, in 1987, two Japanese computational biologists, Saito and Nai, proved that there is a very effective way to recover the geometry of tree. So this is called the neighbor joining algorithm. And then this is indeed one of the papers with the largest number of citations in even biology field. So the number of citations is more than 60,000. And finally, we can describe the image effectively, easily, theoretically. All of the answers are yes. So in 1971, Buneman described the image, and later I'm going to focus on this question. But David Spire and Bront Stumfeld, the familiar names, answered that, well, we can describe the image in a very effective way and theoretically. So that would be one of the main topics. Okay, so now let me explain a little bit more about the third item. Can we describe the image of the dissimilarity map? So here is the classical tree matrix theorem. So that there is very easy obstruction to be a tree metric among many different possible matrices on finite set. So now take 4 different leaves, and then you can draw essentially only 4 different kinds of trees with 4 leaves. Here is one of the examples. If you look at this tree, then let's compute these 3 numbers. D13 plus D24, D14 plus D23, and D12 plus D34. Where if you do the computation quickly, then D13 is A plus E plus C, and D24 is B plus E plus D. So you can check that the sum is A plus B plus C plus D plus 2E. You can do the same job for D14 plus D23. But on the other hand, if you compute the remaining quantity D12 plus D34, then this is simply A plus B plus C plus D, which has to be strictly smaller than the previous 2 numbers. Why? Because it is a positive number. So this is called the 4-point condition. For any 4 subset of leaves, we can compute these 3 quantities, then the maximum of these 3 quantities must appear at least twice. So this is very easy obstruction to be a tree metric among arbitrary metrics on a finite set. And in 1971, by using purely combinatorial idea, Buneman proved that a given matrix vector is a tree metric. In other words, W is the vector is in the image of the dissimilarity map if and only if W satisfies 4-point conditions for any 4 tuples of leaves. Okay, in this case, the matrix tree is unique. Okay, so far everything was about some background and combinatorics. I just want to go slow. Do you have any questions so far? If you don't have any question, then you can thumb up. I think you can do on Zoom. Well, if you have any question at any moment, then please tell me. That's perfectly fine. Okay. All right. Then let's move to algebraic geometry. For first 15 minutes, I didn't say anything about algebraic geometry, but here is the algebraic geometry seminar. So I feel like it's a little bit guilty. So, okay. So the part 2 is about tropical Grassmann. So let me briefly explain very minimal background of basic knowledge of tropical geometry. So the tropical geometry I'm going to explain from now on is a very old-fashioned tropical geometry, and this is a very small portion of the huge field of tropical geometry in 21st century. So now let's fix any algebraically closed field with a trivial valuation if you want to make everything clear. So now let's take any Laurent polynomial P with n variables. Then for this polynomial, we can define the tropicalization of the polynomial trop, which is a map from R to the n to R, which is defined in this way. For the tropicalization trop, for each vector W, the value is defined as the maximum of a rod of these inner products, where U is its power of the variable X. So if you are confused about this definition, then there is a very simple way to interpret a ordinary Laurent polynomial into a tropical polynomial. First of all, because we are using the trivial valuation, you can ignore all constants. That's step 1. And for each addition, replace the addition by taking maximum. And for each multiplication, just erase the multiplication and replace it by addition. Then you will get this formula. Okay. Of course, this is not a very randomly constructed some creature. I mean, there is very deep theory behind it, but let me ignore everything. And I'm gonna use a very old-fashioned maximum convention instead of a minimum, which is very common in these days. Anyway, so that we can define the tropicalization of a polynomial. Then now, this is a continuous map, continuous function as a function whose domain is R to the n. But this is not smooth anymore because we are going to take the maximum of a rod of linear functions. So this is piecewise linear. The associated tropical hypersurface, we can define it, trop of VOP as the set of W in R to the n, such that the maximum in the tropicalization, trop achieved at least twice. So let me draw just one-dimensional picture here. If n is simply 1, then the graph of a tropical polynomial is something like this one. This is a maximum. Okay, I'm sorry, I need to draw a maximum. So this is the maximum of a rod of linear graphs. Then there are several finitely many points where the maximum achieved at least twice. So in other words, the graph is non-smooth. This is this set. The set of these points on the domain is the tropical hypersurface. We can generalize this construction for arbitrary variety in the torus. So now let's take a projective variety X, which is embedded in P to the n minus 1. Then I'm going to use the notation X circle, which is the affine cone intersection with the standard torus in the projective space, in the affine space. Where then X circle is a subvariety inside a closed subvariety inside a torus. Then it would have a defining ideal I. Then the tropicalization of this algebraic variety X circle is defined as the intersection of all tropical hypersurfaces for every polynomial P inside the ideal. So one thing I have to mention here is that it is insufficient to take the generator of the ideal, because there are many examples that we need to add some extra generators. So the generator of I as the ideal theory is insufficient. But anyway, one good thing about this tropicalization is that, first of all, the tropicalization has the exactly same dimension with X circle, and it has an abstract fan structure in R2D. But the fan is usually, and in almost all cases, this is not complete. So now, today, I just want to focus on one example, the tropical Grassmannian. So let's take the Grassmannian Rn, which is embedded in P to the n to the r minus 1 by using the flicker embedding. Then we can think the tropicalization of the Grassmannian GRRn, which is a fan inside R to the n to the r. The idea of the Grassmannian is generated by flicker relations. Well, but because we are thinking about the Grassmannian restricted to the standard torus, it is well known that for this restriction, the three-term flicker relations are sufficient. So we don't need to use all flicker relations. Okay. But now, here is a very informative example. So let's think about the first non-trivial case, Grassmannian 2,4. Well, then there is, this is a hypersurface in P5. The hypersurface is defined by this polynomial. Then now let's take the tropicalization of this polynomial. Then, well, first of all, we need to ignore all constants. So we have 1 and minus 1. Let's forget about the sign. P12 times P34, the multiplication will become the addition. So we need to use P12 plus P34. P13 plus times P24 will be their sum. P14 times P23 will be their sum. And after that, the addition will be replaced by taking the maximum. So the tropicalization of the polynomial P, tropy, is the maximum of these three terms. And finally, with the tropicalization of Grassmannian 2,4, is a fan inside R to the 6, which is the set of Pij's. But now the maximum of these three quantities must appear at least twice. Now you can understand why I try to explain this example. We have 6 different numbers Pij, where ij runs from 1 to 4. And we need to compute the sum of two pairs and take the maximum must appear at least twice. This is exactly the same condition I explained in 5 minutes ago. This is exactly 4-point condition which appears in the space of phylogenetic trees. Okay, so there is an interesting connection. But the only difference here is that there is absolutely no restriction on the value of Pij, On the other hand, in our previous discussion about the phylogenetic trees, the number Dij has to be a positive number. So now I'm going to extend the definition of the metric trees and phylogenetic trees a little bit. So now this is the formal definition. We say an n-leaf phylogenetic tree is a pair of the topological tree with a function L, and G is a tree, fine. And the function L is the function from the set of edges to real number, such that all internal edges must have non-negative length. So we are going to allow 0. And for all end edges, it is possible to have a negative value. Okay, so if you extend the collection of phylogenetic trees in this way, then later it will be identified who is the tropicalization of Grassmannia. Oh, this is a spoiler, but anyway. So now let's fix a topological tree G. Then now let's think about the set of all possible length function L. Then now for all end edge, it may have arbitrary real value. So we need to think R to the n. For all internal edges, it will have a non-negative real value. So the set of all L's over the fixed topological tree has the following construct, which is not strongly convex, but this is a nice construct. Then after that, for each tree, we have a cone. We are going to glue a lot of different cones by identifying tree having length 0 edge, like this example. Then we are going to contract the length 0 edge. Then we can obtain a new tree, something like this. So we have another cone associated to this topological tree. Then we are going to identify these two trees. Then we are going to glue a lot of different cones together. So in other words, we are going to obtain an abstract fan. And this fan Tn is called the space of phylogenetic trees. This is an official definition. Okay, so here is an example of T4. If we have only 4 leaves, then there are 3 different, mostly degenerated topological trees. And for each tree, we have a 5-dimensional cone. They are contracted to the same cone, which is associated to R4. So we are going to glue these 3 copies of R greater than or equal to 0 cross R to the 4 along R4. And this is the geometry of the space of phylogenetic tree T4. But anyway, so in 2004, and this is one of the earliest tropical geometry paper, they proved that the tropical Grassmannian trop GR2n is exactly equal to the tropical, the space of phylogenetic trees. So in other words, if we combine the tree matrix theorem and Spiers-Stempel result, then the dissimilarity map I explained before is injective, and the image is exactly the tropicalization of Grassmannian 2n. Okay, do you have any questions so far? Okay, if not, then let me move on. So now here is a beginning, the start of a new story. So as I have explained so far, the motivation of this problem came from computational biology. But the dissimilarity vector and the dissimilarity map, phylogenetic trees, they are wonderful, but there was one problem. For essentially all of the scientific data, including the distance between 2 species, we have noise. But unfortunately, it turned out that the dissimilarity map is very weak. It is very sensitive to noise. So people try to find some different way to record the distance between a lot of different species, which is very noise resistant. So that was the goal. Because of this, based on this motivation, the computational biologist Factor and Dave Spire defined higher dissimilarity map, which is called phylogenetic diversity in computational biology society, as the following. So now suppose that GL is a phylogenetic tree, a matrix tree, fixing number R, which can be larger than 2. Then now, instead of taking a pair of leaves, we are going to R subset of leaves. So then take one R subset I, then we can think the unique subtree generated by these I leaves. So for instance, if we take A4 set 1, 4, 5, 6, then this last subtree is the subtree generated by 1, 4, and 5, and 6. Then we can define the number di as the sum of all of the lengths of edges appear on this last subtree. So this is the one way to compute the size of a subtree. Okay. Of course, we can do the same job for any full set or any R subset of the set of leaves. Then we can make a higher dissimilarity map. So the R dissimilarity map is defined as the following. And take a matrix tree GL. Then we are going to collect all of di, the size of the subtree generated by an R set I. We are going to use all of them, then we will get a finite length vector. When R is 2, then this is exactly the ordinary dissimilarity map I explained before. But now we have a generalization. And in the same paper, Factor and Spire proved that when R is relatively small compared to the number of leaves, then this generalized R dissimilarity map is still injective. Okay, so we already have the answer for the first question. But they left two remaining very interesting and tempting questions. The first question is that they calculated a lot of examples, and it turned out that the image of dr, which is obviously inside R to the n choose R by definition, but surprisingly, it seems that the image is contained in the tropicalization of Grassmannian RN. So they asked that, well, is it always true or not? After that, the second question they ask is that, is image of dr is a tropical variety or not? If this is tropical variety, then this is the tropicalization of an ordinary algebraic variety X inside a torus. So their question is, describe the algebraic variety X. Well, I have to say that this question is really important, even in computational biology territory, because once we have a tropical variety, then there might be some chance that we can describe a tropical basis, which is a finite collection of defining equations of the tropical variety. So it would be possible, as in the case of this similarity map, such that we can make a finite list of tests that we can say quickly whether the point is inside the image order. The first question, item 1, was proved very quickly by Cruz, Iriarte, Gerardo, and Menon by using many different methods, by using valuation theory, combinatorics, and representation theory. But until last year, the second question was completely unknown. Okay, is there any questions so far? Okay, if not, so now after 35 minutes, finally I can say there's some contribution of me and my collaborators. Okay, first of all, there is a negative result. So even for R and N are relatively small, we found that the answer for the second question is negative. The image of 4D similarity map is not a tropical variety. The proof was surprisingly simple. I mean, we used some computer calculation. But the idea is that a tropical variety, no matter what it is an abstract fan. It has an abstract fan structure, but it is not a random fan. This is a balanced fan. For instance, let me draw just one-dimensional picture. One-dimensional tropical variety looks like this one. But in this picture, you can see that there are 3 vectors for this zero-dimensional cell. Then the sum of these 3 generating vectors has to be 0. Okay. In other words, if you take a generator of each edges of each cone around the d-1 dimensional cone, then the set of vectors cannot be linearly independent. They must be linearly dependent, like this example. We did the computation for this part of the fan, and we found that they are linearly independent. So it cannot be a tropical variety. So, well, this is a really simple computation, but why people didn't recognize this negative result? That's my personal belief is that everybody believes that the image has to be a tropical variety because it has many interesting properties, but it turned out that it is not. But well, if this is the end of the story, then it would be really sad. The interesting thing is that this is not the end of the story. So our claim is that the phylogenetic diversity or the RD similarity map is not the right way to measure the size of subtree. So here is another proposal. So that we decided to call it as a weighted dissimilarity map. So as before, suppose that we have a 4 set of leaves and take a subtree generated by these 4 leaves. Then where instead of taking the sum of all edges lying on this subtree, we are going to take the sum of the distance between pairs of leaves. So here we have 4 leaves. So there are 6 pairs, 1, 4, 1, 5, 1, 6, etc., etc. We are going to measure the length between them, add them together. So as you can see in this example, we have a different value. When these 2, sorry, R is 2, then this is exactly same with the ordinary dissimilarity map. When R is 3, then this is a scalar multiple. But when R is 4, now we have a completely different vector. And now we can define the weighted R dissimilarity map in the same way. And we can define TRN as the image of this weighted dissimilarity map. So everything is parallel. But now our claim is that this is a very, in some way, very good and reasonable definition and list. And here are some reasons. First of all, the weighted dissimilarity map can be decomposed into a composition of ordinary dissimilarity map and a linear map, which is given by a very simple 0-1 matrix. Okay, so this is algebraically tractable. And secondly, this linear map LR is compatible to the tropicalization of a rational map from Grassmannian 2n to Grassmannian Rn, which is defined in this way. Take a matrix representation of one element in Grassmannian 2n. Then for each column, we are going to take a standard Veronese map to R-dimensional vector space. So for each column, we are going to replace it by, degree R-1 monomials generated by these two variables. Then we have a relational map from Grassmannian 2n to Grassmannian Rn. But if we take the intersection with the standard torus in the affine cone, then this is indeed regular. Moreover, we can draw a commutative diagram. There is a monomial map, a Turing morphism from n to the two-dimensional torus, which contains the Grassmannian 2n, affine cone of Grassmannian 2n, to n to the R-dimensional torus, which contains the cone over Grassmannian Rn. And moreover, for each toric monomial map, we can define the tropicalization of such a map, which is exactly the linear map LR described before. So in the point of tropicability, this is very natural, and moreover, it behaves very well. Okay. Moreover, and this is another interesting observation. So now let's take a matrix representation, R by M matrix, which is in the image of the from Grassmannian 2n to Grassmannian Rn. Then now let's look at each column. Then each column is a point. It can be understood as a point in P to the R-1, which lies on a standard rational normal curve. In other words, if we take this matrix and take the columns, then we have n different vectors. Then these n vectors are lying on a single rational normal curve. So in other words, if we define Vr minus n as the set of all endpoint configurations lying on a single rational normal curve, then Vr minus n has some nice theoretic correspondence with the image of Grassmannian 2n. More precisely, we can say that there is a Gelfand-Mapperson correspondence between these two varieties. I have to emphasize that this is not a birational map. Their dimensions are different, but there is a systematical way to make a correspondence between them. I will come back to this topic very soon. But on the other hand, this Vr minus n is by Castelnuovo theorem, where when n is sufficiently large compared to R minus 1, then this is an SLR invariant variety. If you take the quotient, then this is exactly the moduli space of n-pointed rational curves, M0, before taking the compactification. Okay, so yeah, the image of weighted dissimilarity maps can be understood in many different ways. So this is the summary. The image TRN of the weighted dissimilarity map is, first of all, this is the tropicalization of the image of Grassmannian 2n inside Grassmannian Rn, or equivalently. This is also the tropicalization of the Gelfand-Mapperson correspondence to the variety Vr-1n, which is the set of point configurations that lie on a single rational normal curve. And where, as in the case of ordinary R dissimilarity map, we could also show that this is injective. But now this is true for any R between 2 and n-2. So, yeah. Okay. So then let me pause a little bit here. Do you have any questions so far? If you're okay, then please make a big smile. Okay. All right. So this is the last part. So we are working on algebraic geometry. So we are, all of us know that defining equations are in some sense important and interesting. So let's back to the original question. So now let's take a W vector in R to the n choose R. So that we want to understand whether W is indeed in the image of the weighted dissimilarity map. And then we can find a metric tree which provides a tree metric and weighted dissimilarity. So again, in this question, finding a finite list of simple criteria is a really effective and interesting and useful question for both algebraic geometers and computational biologists. So that, we at the same time we know that TRN now have a tropical variety structure. So we can ask the following question. Let's find finitely many equations Fi defining TRN in the following way. So we are not going to calculate the equations of the abstract fan directly. We are going to calculate the equation defining the image of Grassmannian 2n. So we are going to find equations such that the tropicalization TRN is intersection of the tropical hypersurfaces given by the finite set of polynomials. This set of polynomials is called a tropical basis. Well, the existence is well known, but the computation of tropical basis is really difficult to problem. It is way more expensive than Greben basis computation, for instance. Now, we have a partial clue. We already know that three-term frequency relations, they do define Grassmannian Rn. And the image of Grassmannian 2n is contained in Grassmannian Rn. So these three-term frequency relations, they are already defining the image of Grassmannian 2n. So the question is, what other equations should we use? Okay. Then now, the reason why the Gelfand-Mapperson correspondence observation is really important and interesting is the following. So VRN R-1n is an SLR invariant variety by definition. On the other hand, the other side, the image of Grassmannian 2n is the torus invariant. Now the Gelfand-Mapperson correspondence actually tells us that on the defining equations, coordinate ring level, every SLR invariant equations of VR-1n correspond to a torus invariant equations of the image of Grassmannian 2n. So on the set of defining equations, we can find the real correspondence. So now our strategy is, let's find the equations of point configurations, the space of point configurations, and take the Gelfand-Mapperson correspondence and tropicalize them. So now this is really a classical algebraic geometry question. Let's think about the variety parameterizing endpoint configurations in projective space R-1 lying on some rational normal curve. This is an algebraic variety. Find the set of defining equations. Okay, so now let's start with the simplest example, V26. So this is the set of 6 points on projective plane P2, lying on a relational normal curve in P2, which is a smooth cone. Well, then this equation was known even 19th, even 18th century. So this is an open dense subset of an irreducible hypersurface given by this equation, P1 to 5, blah, 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 where Pijk is the determinant of ijk points. Okay. But one interesting thing we observed, and it turned out that this is really important, is that the variety V26 is by definition S6 invariant. But on the other hand, this equation is not. Even if this is a hypersurface. The reason is simple, because free coordinates are not linearly independent. There are many relations. So that we need to understand how to find all representatives of the same equation of the same hypersurface. So here is the combinatorial description. So now let's take a finite graph G, which is a graph whose vertex set is 3 subsets of the set of 6 numbers. And take 2 elements, they are connected, 2 vertices are connected if and only if the intersection has 2 elements. So then this is the example, a part of the graph G, not all of them. So each vertex corresponds to a 3 subset. And I'm going to connect them whenever the overlap has 2 elements. Then this graph is somewhat complicated but finite graph. Then now let's take a subgraph of G, which looks like a cube. So this is one example of cube. There are exactly 15 different cubes in this graph G. Then where for each cube, a cube is a biprototype graph. So we can color all of the vertices with 2 colors, such that the 2 adjacent vertices have different colors. And now we can construct a polynomial in the following way: the product of all blue variables minus the product of all red variables. Okay. Then indeed, this hypersurface can be this equation can be understood in this way, which means because there are exactly 15 cubes, there are exactly 15 different representations of the same hypersurface. Okay. Then now, this observation was really helpful later. So the next topic I'm going to tell you is that starting from V26, which is very classical example, how can we construct the equation for the general VR minus 1n? So the key technique is to apply Gale transform. So the linear algebra definition of Gale transform is the following. Let's take an R by N full rank matrix A. Then the Gale transform GA of A is another matrix B, which is an N minus R by N full rank matrix, such that A times B transpose is 0 matrix. Well, and this is a very simple elementary object. So you can explain it in your linear algebra class. But now, first of all, the Gale transform is well defined only up to GLR action, because if you permit rows and columns, then obviously we will get some different equation. But anyway, so there are 3 important theorems. First of all, the Gale transform is involutive up to GLR action. Fine. Number 2, up to a scalar multiple. This is very interesting. So let's take a subset, R subset of indexes. Then we can compute the Flickr coordinate. Then for Gale transform, you may compute the Flickr coordinate of the complementary index set. Then these 2 sets, these 2 Flickr coordinates are essentially equal to each other. And I mean, they are different only up to scalar, which is independent from the choice of I. Finally, this is a classical result of Gopa in 1970s. Let's take a full rank matrix A. Then if you take each columns and project divide them, then we have a point configurations defined by column vectors. Then the point configuration is relying on a rational normal curve. Surprisingly, if and only if the Gale transform is relying on a rational normal curve. This is really surprising because the Gale transform is relying on a different dimensional projective space. So there is a very strange, mysterious connection between the point configurations on 2 different dimensional projective spaces. So now, let me briefly describe how we can cook up the equation of VR minus 1n, starting from the equations of V26. So our claim is that this is sufficient. So let's start from a point configurations on R-1 dimensional projective space. For any subset I, we can take the subconfiguration. So start from a point configurations relying on a rational normal curve. First of all, we are going to forget several points. Then now we are going to apply the Gale transform. Then we can make a point configurations relying on a projective plane P2. We are going to forget more points. Then we have 6-point configurations relying on rational normal curve. So we know that it must satisfy the equation of the following form. Well, then this is an equation of subconfiguration. So the ambient configuration must satisfy the same equation because this equation is independent from the choice of other points. Then now we are going to apply the Gale transform again. Then we have another point configurations. Finally, we are going to recover several more points. Still, they satisfy the same form of equation. And the result of my collaborators is that a point configurations in VR-1n, the point configuration is relying on a rational normal curve if and only if it satisfies these kind of equations for all R-R+3 subset of n and all 6 subset of j and all cubes defined on the 6th set j. So essentially, there is only one kind of defining equation. So we are almost done. So now let's think about the tropicalization of this defining equation. The tropicalization of the variety defined by this polynomial. The interesting thing is that this polynomial is a binomial. This is a difference of two monomials. So if you take the tropicalization, then all multiplications becomes addition. And we need to take the maximum between them, and the maximum must occur twice. But because there are only two terms, the maximum occurs exactly twice if and only if these two terms are same. So in other words, the tropicalization of this binomial is simply a linear space. Okay? So we can cook up a lot of linear equations which satisfies, which cut out the tropicalization of the image of Grassmannian 2n, which is the image of weighted R dissimilarity vectors. So let me rephrase the theorem again. Now we do have a complete set of defining equations. A vector W is in the image of weighted R dissimilarity map, if and only if it satisfied 4-point conditions and it satisfied linear equations from cubics. So the number of equations are a lot, but we can check that and choose 4-point conditions and n choose R minus and choose 2 linear equations are sufficient. This is a matter of computation. Finally, one very interesting thing is that the set of equations for the image of phylogenetic trees is characteristic free. So even for characteristic 2, we can get the same set of defining equations. But on the other hand, tropical Grassmannian does depend on the characteristic. This is a classical result of spiral stuff. Okay, so then let me finish it with some questions. I just want to raise several questions for students and for professors who have some students who are interested in tropical geometry stuff. It turned out that the set of point configurations on a curve, this is a very classical object, but at the same time, it has a very interesting structure in the point of view of tropical geometry. So we investigated the genus 0 case. The next example is the elliptic curve. for planar elliptic curve, what is the tropicalization of the set of point configurations on an elliptic curve? Can we describe it as a modular space, as a parameter space? This is one possible question. And or we can extend the same story to higher dimensional one. So a tree is a one-dimensional contractible simplicial complex. Now let's think about the set of contractible higher dimensional simplicial complexes like 2-dimensional, 3-dimensional, etc. Is it a tropical geometry? Is it a tropical variety or not? If it is, can we describe the tropical variety by using defining equations? And finally, in computational biology, the following question is missing, and this is a really important question. Can we make a neighbor joining algorithm based on our new weighted dissimilarity map? Okay, so I'm gonna stop here. Thank you very much for your attention, and stay healthy.
Okay, thank you.
Thank you.
Is there any question? Yes. Junkai?
Yes. So
Yeah.
So I'm curious that is there any kind of concept of degeneration? I mean, for example, if you just change your length little by little, and what's going to happen to the structure?
Well, the nature of tropical geometry, the tropicalization this is taking all possible degenerations in some sense. Okay, so because one way to define a tropical variety is using valuations, and valuations naturally they encode some sort of degeneration information. So yes, in some sense, yes, but at least in this picture, we could ignore the degeneration idea completely because everything is over trivial valuation, as I explained before. But if we use some different valuations, yes, sure, there will be more things that people can say.
Thank you.
Okay, Ife, you have question?
No, I don't have questions. Thank you.
Okay. Are there any more questions? So one of your last 3 questions or problems, elliptic, point configuration on elliptic curve. The elliptic curve has a group structure.
That's right. Sure.
So yeah, so point configuration, interesting to see, how is related related by this.
Yeah, that's a great question indeed. I would like to say that as far as I know, this is one very important missing piece in tropical geometry at this point. So by nature, the tropical variety behaves very well with the torus section. However, for any tropical variety, it is very difficult to define a tropical group action. So as far as I know, there have been several attempts, but I don't think that there is any satisfactory theory about the group action, how we can define the group action, even the tropical group. What is the creature? So that would be really interesting question, and I personally really believe that this is a really wonderful question. And it would be really nice if somebody can find a right definition of one tropical group. So my answer is, honestly, I don't know, but it is really interesting question.
Okay, so any more question? If not, then let's thank the speaker again for his wonderful talk.
for your